Hi and welcome back. I just wanted to show you how to convert a recursive problem into an iterative problem. So I just solved lead code 94, which is how to do the in-order traversal of a binary tree. You should be able to see that in the previous video. And this is kind of the code that we wrote, where you do the in-order traversal. And I also explained that in order to change it to a pre-order traversal, you basically just change the position of where you emit the node. Either you do that before you insert the left subtree, that's a pre-order traversal. If you emit the node's value between processing the left and the right subtree, that's an in-order traversal. And if you emit the node's value after you've processed the left subtree and the right subtree, that's a post-order traversal that gives you. Now, any recursive problem can be turned into an iterative one with a stack. That's just a scientific fact. And it becomes easier when you have a tail recursive problem where your recursive call is just, you just have one recursive call, and that's the last function call inside your recursive method. That's the easiest case. Now, here we have two recursive calls, and I'm just going to show you how you turn that into an iterative one with a stack. So let's just make sure that this code works as intended for the in-order traversal, just to demonstrate it. So it does. It works on all our examples, returns the right ordering of the node's values. And we're going to implement another little method that's called def it helper, so for iterative helper. And we're also going to take the node and a result list. So just so that we have the same signature as the DFS helper method here. And we're just going to return the iterative helper instead of the def first search helper. And well, if you want to turn a recursive problem into an iterative one, you have to do manually what the program otherwise does for you. Every time you call a function recursively, it will put the current context of this method call, the original method call, onto the stack. And it will enter this method and a new context is created. So on top of the stack. And when you return from this call where we process the left subtree, we are restoring the previous state that we had before we entered the recursive call, right? So we are popping the stack back into our, well, it comes back into our view. What we pushed down the stack before now becomes top of the stack again. So one thing that we will always need to have is a stack. And that is just to store the state. And in the beginning, well, we have nothing to do. But when we want to iterate over, all the nodes in the tree, we should probably just initialize our stack with the root. So here we should actually call that root. And now what we do is we iterate as long as we have items on the stack to process. So that's what we'll do. And now we're going to fetch the next piece of work from the stack. It's similar to when we call DFS helper. DFS helper basically just gets the next node. It also has access to the result, but we're not too worried about that because we could put result outside here so that it's not part of the call. So we could actually do something like this. Non-local result. There you go. So when we enter the loop, we have to get our parameter that otherwise the recursive function gets. So what we'll do is we say node, or better we say node equals stack.pop, because we're popping it from the top of the stack. So now we can do exactly the same thing as we did before, right? We can process the left subtree, we can process the right subtree and decide where and when to emit the node value. Now, as soon as we want to go into a recursive call, we first need to put the next operation that we're going to do back onto the stack. So if we want to say, if we want to process the right subtree last, we have to insert it first into the stack. So, whoops, typo. Node.write. So if we put that onto the stack, and then we put the left one onto the stack, that means the next time we call pop, we're actually getting the left subtree to process, right? So that is basically what we do. And if we do it this way, we will iterate through all of our nodes exactly as we would in our recursive approach. We would, well, we put the root on the stack. Then in the loop, we pull out the root. We push the right node onto the stack and the left node onto the stack. Now in the next iteration of the loop, we will pop off the left the node to the left of the root, and we will put its right back onto the stack and its left. And then in the next iteration, we will process the node with the value 4. So, and then when there's nothing here to process, right? Well, we will pop the next node from the stack, and that was this one. So now we're starting to process the subtree that starts here. We process that one, we process that one. Now the next node on the stack is, well, it's the 3. So this allows us to do exactly the same thing as we had recursively here before. But we, of course, we need to pay attention to, not running into none values. So if node is not none, then we're going to continue to process. Otherwise, we could be putting like a null value or a none value if there is no left or right subtree onto our stack. That's pretty much that. So we now return a result. All we need to do is basically we need to decide when to append stuff to our result. Well, if we do it right here, that's probably not smart because we're adding a node we're adding the left and the right subtree, but we're just adding the node as well to, to our result list. So regardless of where we place this here, it's always going to be a pre-order traversal because we're not processing left and subtree yet. That happens in the next iteration of the loop. So if right now we add the value of the node to the result, it's a pre-order traversal always. So how do we get around this? Well, the stack tells us what item to process next. So we could also use the stack. Sorry, this should be append, not pop. What we could also do is we could just append the value of the node to our stack, right? .append node.val. So now that means when we add node, that means the next 3 items to process are from bottom to top. First the left subtree, then emit the node value, and then the right subtree. The only thing we now need to do is, because the stack now contains 3 node objects as well as numbers, we need to distinguish, if this is actually a number or if it's not. So we have to add another little if statement here. If is instance node of int. Well, in that case, we actually have an in value. So what we'll do is we will add it to our result. Result.append and node. And this is really just a node value, right? Otherwise, we're going to continue with that processing. And yeah, that should be everything. So if we run this now, we actually get the correct result, and we're getting the in-order traversal. And to demonstrate you, if we put this maybe at the bottom, then we should get a post-order traversal. If we put this first, we should get a pre-order traversal. So let's run this as the test. The test will fail, but we will see in the output the pre-order traversal. So let's do that. Let's see if we get the pre-order traversal. So pre-order is 1, 2, 4, 5, 6, 7, 3, 8, 9. 1, 2, 4, 5, 6, 7, 3, 8, 9. That's exactly what it is. And just to test the post-order traversal. So the post-order traversal should be 4, 6, 7, 5, 2, 1. 4, 6, 7, 5, 2. 5, 2, 9831. Yeah. Okay. Yeah. So yeah. So easy peasy. It's worth to really try to understand this, and with a little bit of practice, you can turn your own recursive problem into an iterative one using that principle. And the binary tree traversal is a really nice example because it has 2 recursive calls, and you need to manage on your stack. Basically, the stack is kind of your work queue, right? It tells you what to do next. In the recursive approach, you're doing the next thing right away. But if you want to do it with the stack, you just put the work items on order. So if we want to do the left tree first, we need to make sure that the left node to process is the top element on the stack. And then we want to emit the value. So that's the element before that on the stack. And then finally the right one. So the order here is reversed of the work items that you want to do. Yeah, that's pretty much it. I hope you found this useful or helpful. I encourage you to practice a little bit. And also try other problems. For example, the Fibonacci number problem is an excellent choice because there you only have one recursive call. And you can also have a version where you have a tail recursive call. And that is the easiest recursive type of problem that you can turn into an iterative one. So yeah, have fun experimenting with that. This is really basic computer science, and if you understand those principles, it'll be much easier for you to switch between an iterative and a recursive implementation, and you will also get much better at judging which one might be the one that is easiest to implement. Typically, the recursive one is the most easy to implement, and the iterative one is often optimization when you're computing a result that is shorter than the depth of your call stack when you do this recursive descent. All right, that concludes the video. Thanks for watching.